Okay, these are some of your notes for section 5.6, part 1, and we're going to look at simplifying radicals. Now, what we're going to do in section 5.6 is just change the form of how a problem looks. It's going to still be the same answer if you put it in the calculator and you got a decimal approximation for it. You'd get the same thing whether you put in the original problem or the answer. So really all we're doing is changing the way that it looks. Okay? First thing we're going to look at is simplifying radicals. Now, you've done this before. You've done this in geometry. It's where we take a radical and we break it down. We want to take the square root out, and that's what you're familiar with, is square roots. In section 5.5, we changed it up a little bit, and we talked about what if the index is something other than 2. Well, we're going to be doing the same thing here with simplifying radicals. We're going to go through and we're going to work out these problems and we're going to simplify them as far as they could go so that our answer is in the simplest form. Okay? We're just going to change the way that the problem looks. So, a couple things to remember and that we're going to recap from section 5.5. This n here is your index, and it's extremely important to pay attention to when you're doing these problems today, because that's how many you want in a group to take out. Or you want to look for something squared, something cubed, something to the 4th power. That tells you what column to look at in your chart. Now, B is the radicand. It's what's underneath. It's what you're going to be simplifying, okay, to get to your answer. That's what's going to be broken down. The other important thing you need to remember is absolute values. And you only need absolute values on variables when you start with an even index, and when you get your answer, you have an odd exponent. Okay? That's when you need to put absolute values around that particular variable. Okay? When you start with an even index, you have an even index for the problem, and the exponent on your answer is odd. Alright, we're going to do a couple examples. We've got 6 here. Most of these first 3 are all going to be square roots, which should be pretty easy for you, and then we're going to change the index. So, the first one is the square root of 75. What we want to do is we want to find the biggest perfect square that goes into 75. So if you have your chart, you can look down the square column, okay? Remember, our index is a 2. It's not written. It's understood to be there. We can look down the square column until we find a perfect square that goes into 75. Well, it's 25 and 3. 25 is the perfect square, so the square root of 25 is 5. That moves out front. 3 is not a perfect square, so it stays underneath. And there would be the simplified answer. Okay, 5 square root 3. Let's look at the next example. We have the square root of 45a cubed. Now we have a variable in there. It changes a little bit when we have a variable. Let's break down the number first. We want the biggest perfect square, because our index is a 2, that goes into 45. So we look down our column, 9, and then 9 times 5 gives us 45, and 9's our perfect square. Alright, so we're going to start with what goes out in front. A 3 is going to go out in front because it's the square root of 9. The 5 is going to stay underneath because it's not a perfect square. Now let's deal with the variable. To figure out the variable, remember we take the exponent and divide it by the index. Well, 2 goes into 3 one time with a remainder of 1. This means that 1a is going out in front, a to the first. The remainder means 1a stays underneath, okay? So this becomes the exponent on what goes out in front, and this is the exponent on what stays underneath. Now, since we have a variable, we need to check for absolute value signs. We have an even index. Our index is 2, and we have an odd exponent on our answer. So a needs to go in absolute values. And then here is the answer to our problem. 3 times the absolute value of a, square root of 5a. Okay? The next example. We also have variables, so we're going to have to check for absolute values at the end. But we're going to treat it the same way we did the second example. Let's break down the number first. We have 25, the square root of 25, a to the 4th, b to the 9th. 25 is already a perfect square. Okay, so it's going to completely move out in front. We don't have to worry about breaking that down. It's all going to move out in front. Now with two variables, we're going to do each one. 4 divided by 2 gives us 2 remainder 0. That means that we have an a squared out in front and no a's underneath. Let's look at the b's now. 9 divided by 2 is 4 remainder 1, which means b to the 4th. 4 b's go out in front, and 1 b stays underneath. Now we have to check for absolute value signs. We do not need absolute values here because we have an even index and both exponents are even. One's a 2, one's a 4, so we don't have to worry about absolute values in this case. Okay? So those are the first three examples. Those are using square roots. That should be something you're vaguely familiar with. Now let's go on to when the index changes. Let's look at our next example. We have the cube root of 8,232. So what we want to do is we want to look down our column and see if we can find the biggest perfect square that goes in, the biggest perfect cube that goes into 8,232. Now that might take you a while, so I'm going to approach this one a little differently. We're going to use a factor tree. What we're going to do is we're just going to break down this number with what we know, okay, by looking at it. It's an even number, so we automatically know it's divisible by 2. So now we can say 8,232 divided by 2 is going to be 4,116. So those two numbers multiplied together give us 8,232. Now we're going to do that again, but this time we're going to use 4,116. We're going to break that one down. It's also divisible by 2 because it's even. So if we divide that by 2, we get 2,058. We're going to continue to do this. Let's break this one down. Divide it by 2. That gives us 1,029. Now we have a number that's smaller to deal with. We're going to look in our chart for something, the biggest cube that goes into 1,029. And that's easier to deal with. Our numbers aren't as large. When we do that, we can figure out that it's 3 and 343. Alright, so I'm going to rewrite this a little bit. I'm going to make this, we had 1, 2, 3 2's, so 2 cubed times 3 times, and 343 is really 7 to the 3rd. That's what we end up with. And when we factor this down, we get the prime factorization. Now I wrote it that way for a reason, because this is a group of 3, and this is a group of 3, which means I'm going to take one from each group out in front. So I'm going to take a 2 and a 7, and when I take more than one thing, I have to multiply them together. And I'm going to leave whatever didn't have a group, the 3, it's not a perfect cube, underneath. So now I have 2 times 7, which is 14. The 3 stayed underneath, so we have 14 cube roots of 3. And that's how we would solve that problem. That's a different approach because our number was so large, and you can do it that way if you would like. It just realize it takes some more work, a little more time to do the problem that way. Alright, let's look at our next one. We have the cube root of 250s squared. Well, we're going to look down our column. We're going to find the biggest cube that goes into 250, and it's 125. 125 times 2. Okay? 125 is really 5 to the 3rd power. So 5 is going to go out in front. The cube root, the 2 is going to stay underneath because it's not a perfect square. And now we're going to deal with the s. Well, 2 over 3. 3 does not go into 2 evenly, so it's 0 remainder 2. That means both s's will stay underneath. So the answer to the problem is 5 cube roots of 2 times s squared. Okay, in that case, the variable didn't go out because our variable was smaller than our index to begin with. We've got one more example here. Now we do have a variable, we have an even index, so at the end of the problem we are going to check to see if we need absolute values. Remember, we should be paying attention to that as we do these problems. Alright, we've got the 4th root of 48x to the 6th. So we're going to break down 48. We want the biggest thing to the 4th power that goes into 48. So we look down our column, we figure out we've got 16, that's really 2 to the 4th, times 3, which goes into 48. That means that we're going to take a 2 out in front, because the 4th root of 16 is 2. Now we're going to deal with the variable. 6 divided by 4 is 1 remainder 2. That means we have 1x out in front and 2 x's that stay underneath. Now we do need to check for absolute values. The x does get absolute values because it has an odd exponent with an even index. So there's the answer to our problem. 2 times the absolute value of x, 4th root of x squared. Okay? And those are your notes on simplifying radicals.